Hello, everyone. Welcome to this first discussion on a course overview for microcontroller programming for Power Electronics 1. My name's RJ, and in this video, we'll just be going over the course. So here are some objectives of the talk. We'll be providing a tentative schedule on topics, state our goals for the series, review elements of an embedded system, introduced the C2000 product line, which is the line of microcontrollers offered by Texas Instruments that we'll be using throughout the course. And then we'll be suggesting material to purchase in order to follow along with the course, and then provide some references for further reading. So here's just a tentative schedule. This is for a 10-week treatment of this topic. So you can see we're talking about the course overview first, and we're slowly progressing through different parts of the microcontroller and different parts of um, programming the microcontroller itself as well. So in the quarters after this 10-week treatment, we're hoping to look at specific applications in more detail and then eventually build up a digitally controlled power converter, right? So this is just an example of one of the applications that TI has posted on their web page. So the goal for this first series is to first off build knowledge in the programming of microcontrollers. And so this is kind of intended as a first course in microcontroller programming. So those of you that do not have any experience whatsoever should be able to follow along, I think. And then second, we want to learn and apply control theory to digitally controlled power electronics. And so we'll be taking a look at specific applications of the different peripherals that are available on the particular microcontroller. So an embedded system is a control platform based on programmable logic. These are just some examples of popular and trendy applications of embedded systems. Right, so on the left, we have an electric vehicle that's connected to some kind of charging station. In the middle here, we have a motor, and on the left here, we've got some photovoltaic system that's converting, energy from the solar panel into electric energy that can be used by electric vehicles. This is not an exhaustive list of applications, but these are just some trendy ones that were provided in this reference that we'll take a look at later. So microcontrollers are versatile programmable logic devices that embedded systems are built around. Um, so in this picture, we can see the actual microcontroller itself, along with a bunch of different peripherals that are set up around it, and then a bunch of pins that are actually broken out so that we can actually use and test the microcontroller itself. So this is an example of a launch pad device that's provided by Texas Instruments, and it's usually used in building up prototypes or experimenting. And so we'll be using one of these, but we'll get into that later. So just some key elements of a microcontroller are the CPU, right? The clock speed, which is directly associated with that CPU. Um, Random access memory, so that's RAM, and then data memory, the general purpose input output pins, and then there are analog pins and the pulse width modulator. And so we'll be taking a look at all of these different things throughout the course, but just to give you an overview of what the microcontroller itself entails. So here's a good little picture that I also pulled out of one of the reference textbooks. So programming microcontrollers can be classified as low level, intermediate level, and high level. So this was done by that textbook. They classified at these levels. So low level is assembly, right? So some of you may have experience with digital logic and that kind of design on FPGAs and writing assembly code, right? like loading up registers, having an arithmetic logic unit to add different things, and a program counter, that kind of level. Intermediate level is based on the C programming language for the most part. So we write code in C, and then an IDE is used to then compile and link it into machine code, which is then, programmed onto a microcontroller. And the IDE also provides a means for debugging, right? So actually stepping through all the different instructions. And then at the high level, we have object-oriented languages and a toolbox, much like so MathWorks provides a means of programming microcontrollers in a drag and drop environment. We won't be focusing too much on this high level, but we'll be taking a look mostly at intermediate level programming. And so TI offers a lot of free software development tools to support this intermediate level, including different libraries and um, applications that automatically kind of generate code. But once that code is generated, you still need to leverage it and be able to use it, in that intermediate level. So this C2000 is a product line of high-performance microcontrollers that are widely used in digital power. Um, and so we'll be taking a closer look at this Delfino family of the C2000 line. And these are just some of its specifications. I don't want to read over all of that, but it's there for your reference. So microcontrollers provide a means of sensing, processing, and actuating in feedback control systems. So presumably some of you have had a course in control theory, but if not, this is kind of just a high-level overview of a feedback system. So typically speaking, we're trying to track some kind of reference. For example, in a DC to DC converter, this could be your target voltage, that you want to have on the output. So maybe we were trying to regulate to 5 volts at the output or something. So we have a 5-volt reference, and then coming back from the actual system is a measurement, right? And then this goes through some sensing processor-based circuitry, such as an ADC, and that sensed measurement is then compared with the reference, usually subtracted from it in order to generate an error signal. From that error signal, we apply some control algorithm and then actuate some devices. So this is usually in the form of modulating the pulse width, um, of some kind of an on and off switch. So this is just like a very high level overview of feedback control. We'll obviously be getting a closer look later on in this course. So again, the main blocks here are sensing, processing, and actuation. And the C2000 microcontroller has a lot of features for feedback control, with regard to these sensing, processing, and actuation blocks that we'll take a closer look at. This is from that textbook again. I'm not going to read this. So once we become familiar with the microcontroller programming, we can take a look at reference designs. So TI has a lot of good reference designs that walk you through the process of how you can leverage some of their tools to go and actually build power electronic systems, among other things, right? So they have motor control systems as well that you can take a look at. But for this course, we're focusing in on their digital power suite. So now here we have some suggested material to purchase. First off is this launch pad. Um, and I said that this is required mostly because, we'll be having some hands-on demonstrations of how to program this. And so it'd be good for you to have one to follow along at the very least. And so this is $39 on TI. So you can purchase directly from them or elsewhere if you think you'd rather purchase from DigiKey or Mauser or something. And so if we click on that, it looks like this. Um, so here it is in red. We actually had a picture of this earlier in the slide deck, and we'll be talking a lot more about this next week. And the other thing I recommend to purchase is this Analog Discovery 3. So I linked this academic pricing link. So typically this pro bundle comes in at about $409, but with academic pricing you can knock that down to $279, which is really good. And so this is a really small green box that you can connect to your laptop or PC. And it comes with this really neat software that allows you to use this little box as a function generator, power supply, and oscilloscope, among other things, which can be really useful, especially when you're designing your own electronics in the future. So I recommend that you purchase that. And then, so now we're just talking about next week. So next week we're going to be taking a look at the microcontroller core and its peripherals. And so here are the references. First off, this is that textbook that I mentioned. This is pretty good. So through the library, at least at Cal Poly, we have access to a lot of books offered by Taylor and Francis. So it's a publication group. Um, and one of those things that we can access is this book. So we have full access to this entire book. So they focus more on coding with MATLAB and Simulink, but I found a lot of their introductory chapters to be useful, at least for the creation of this presentation. So if you're looking to read more, that's a good reference. Um, so here are some of the examples from Texas Instruments. I think these are the reference designs, right? So we've got a whole section on motor control, whole section on digital power, and within those sections, a bunch of really good reference designs. So for example, if you wanted to make a DC to DC converter, you know, here's some reference designs that they have. They usually have good technical documentation. So this is just a test report, it looks like. But in that test report, they'll usually talk about the design process. It looks like in this one, they're actually just providing physical test data, which isn't too useful, but a lot of the other designs do actually have a full design process within them. So, you're welcome to check that out. And then C2000ware, um, this is a software package that we'll be taking a look at throughout the course. You don't necessarily need to look at it right now. We'll be taking a much deeper look into it next week, but it's good to be aware of that. And I think that's all I had for this video. So thanks for tuning in. I'll see you guys next week.